Hello, AP Stat students. Today we're talking about means and standard deviations of random variables. We're going to revisit the example from our introduction notes, where the number of items a given salesman sells per customer is shown below in the table. So this is a discrete random variable, and we'll be finding means and standard deviations of discrete random variables. So to find the mean of this random variable, we simply multiply each value the random variable x can take on by its probability of occurring. So the formula is as follows. So we're finding the mean, and another name for the mean is the expected value, which is denoted as e of x. So you'll see that that notation is here as well, and we'll discuss what that means in a second. But here's the formula, and we basically take every value of x and multiply it by its probability, and then once we have all those products, we add them together, and that will give us the mean or the expected value. So basically we're going to be multiplying these pairs together, which I'm circling in the table, and then we'll add up those products. And the best way to do this if you're doing it by hand is to make a table like the one below. So I listed off all the values that x could take on from 0 to 6, and then I also put in their probabilities next to it. And then all we do is we multiply these together. So these are pretty easy to do by hand, but I'll show you in a second how we do this on the calculator. So we just take like 0 times 0.2 is 0, 1 times 0.35 is 0.35, 2 times 0.15 is 0.30, and we just keep multiplying those pairs together, okay? Then with this last column, this third column, we simply add those together, and that becomes our expected value. So the mean or expected value, which is this formula, is 1.84. So what does this mean? And of course, in statistics, we're always looking for interpretations, okay? Like, what does this mean in real life? So the interpretation is we interpret this value to mean that on average, the salesman can expect to sell 1.84 items per customer. Now, obviously, you can't really sell someone 1.84 items, okay? You'd have to sell them one of the numbers in the table, so anywhere from 0 to 6 whole numbers. So what does this mean? Well, the bottom paragraph says it's impossible to actually sell 1.84 items to someone. You can only sell whole numbers. But if the salesman kept track of sales over the next month, he or she would or should average selling 1.8 items per customer. And you can think back to the earlier probability units with the law of large numbers. The more people the salesman sells to, the closer his average or her average should be to 1.84 items per person. Okay? So that's what the expected value means. And you guys are going to need to be able to make this interpretation. Okay? So you're going to have to be able to make this or come up with this sentence on your own. Okay? So you have to be able to interpret the expected value in the context of the problem. Now, the other thing you want to be able to do is compute the standard deviation. Okay? And this is a little harder to calculate by hand. Like with quantitative data, we will compute the variance first, then we're going to take the square root of the variance to find the standard deviation. So here are the formulas. The variance formula is right here. And basically what we're going to do is we're going to take every value that the random variable x can take on, and we're going to subtract the mean from it. And that's exactly what we did in our old standard deviation equation, if you think back. It was this. Okay, so we would take, we used to take x minus, or take the mean away from x, and then we'd squared those differences, and then we added them up, and then we divided by how many we had, and then we took the square root. So we start out that same way here, x minus the mean, and then we're going to square those to turn them all positive and kind of large. And then instead of dividing by n, we are going to multiply them by their probability. Okay, because each one's going to contribute to the standard deviation based on how often it occurs. Okay, and then we're going to add up all those products. And before we take the square root, that's called the variance. And then the bottom equation is exactly the same, except we put that variance equation under the square root. Okay. So again, standard deviation is the square root of the variance. So again, if you have to do this by hand, we would do this by using a table. Okay. So I have another column with all my x's in it, and our average was 1.84. So I would take each x and subtract 1.84, the mean, from them. So I did that in the second column, and these are my values. Some are positive, some are negative. So I square all of those, and I also multiply by the probability of each of them happening. Again, I took those probabilities right off the table above. So I would do this calculation and get 0.67712, and et cetera, et cetera. So I would do that calculation for every value. And then the sum of this last column over here, that's called the variance. Okay, so on my calculator, I added those up quickly, and I got 2.5744. So that's the average spread of the squared distances around the expected value. And I wanted to find the standard deviation, so I take the square root of the variance, and I get 1.6. So the interpretation of the standard deviation is that the salesman can expect to sell 1.84 items per customer with an average difference per customer of 1.6 items. Okay, so the average variance in how many items that this salesman sells per customer is about 1.6. Okay, so sometimes they can sell up to 3, and sometimes they can sell as little as none. Okay, anything beyond that doesn't happen very often. Okay, if you look on the chart of probabilities, the salesman can pretty much expect to sell 0 to 3 items most of the time. Okay, it is possible to do this on your calculator. So next, I'm going to show you how to accomplish this on your calculator. So again, I have the same table We're going to use the salesman information. So the first thing you do is you enter the data into L1 and L2 on your calculator. So remember, you go to Stat and Edit for that. And if you have some data in your calculator from previous problems, what you can do is arrow up to the title of the list and then hit Clear and Enter. Okay, and that will clear off that list. Also, when you go into Stat, one of the things on the menu is Clear Lists. So you could also just do that first and just clear off all your lists. So you have 2 choices. Anyway, so you enter your data into L1 and L2. Then the second thing to do is you go to Stat and then slide over to Calculate, and then stay on that first choice of one variable stats. This is the same place we used to go to find the mean and standard deviation of quantitative data. Then on the next screen, bottom left, as you're entering these, you want the list to say L1. L1 is where our random variable x values are located. And then the frequency list, we want that to say L2 because that's where the probabilities are. That's another way to say like how frequently does each one occur. Okay. If you're on an 83 calculator, when you do the one variable stats, it'll come out onto your screen, and then you'd want to do L1, comma, L2. Okay. Now those L1 and L2s are located above the 1, 2, 3, 4, 5 keys. They're very small and in blue, and you have to hit the second button to get it. So when you want to put this L2 as the frequency list, you'd actually hit the second button and then the 2, and that'll put in the L2. Okay. Then you'll just hit the calculate button, and on this last screen you'll see the mean will show up in 2 places. Those 2 numbers should be the same. If they're not, you did something wrong, like you typed in the incorrect percentage for one of the probabilities or something. But those 2 should be the same, and those are the means or expected value. And then the standard deviation is sigma x, and we rounded that to 1.6 in our problem. Okay, so you can always use your calculator. In fact, I recommend you use the calculator instead of doing it by hand. Okay. Now, I'd like to show you one more example of how this can be used. Okay, so this example says, suppose we're running a carnival game where the player rolls a 6-sided die, and we pay them the number of dollars that they roll. So if they roll a 4, we give them $4. If they roll a 6, we give them $6. If they roll a 1, we give them $1. Okay? Kind of an easy game to play. We're going to assume it's a fair die, so there's no trickery involved here. We're going to create a probability distribution for this random variable x, the amount of money the player can win. So, what are my options for x? Well, the player could win $1, $2, $3, $4, $5, or $6, right? And then the chance of rolling any of those are 1/6 every time. So this is one of those problems we could actually do this by hand because they're pretty easy multiplications. Remember to find the expected value. We just are going to add up x times p of x. So I'm going to multiply these together. So that's 1/6, 2/6, 3/6. I'm just multiplying these pairs together. 4/6, 5/6, and 6/6. And then I'm going to add those together. So this one is equivalent to 1. If I put this together with this, that's 1. If I put this one together with this one, that's 1. So I'm at $3. And then the last one is the 3/6, which is a half. So my average or expected value is going to be 350. Now to find the standard deviation, I am going to use my calculator for that. So I put the x's in L1, and the p of x is in L2, and do the one variable stat thing, and I get a standard deviation of 1.71. Okay, so I'm going to interpret this expected value. So if a player plays this game many times, and that's many, many times, they can expect to average winning 350 every time they play. Now, think about this for a second. In this game, can you actually ever win 350? Well, no, because you can't roll a 3.5. Okay, you could win $3 or $4, but you can't win 350. But what this means is if the player played many, many times, and many, many times could be thousands of times. Okay, if the player kept track of how much they won, they would average 350. Okay, and that's the key part of this, is that they'll average winning 350. Okay, now the last question says, if you were in charge of this game at a carnival and you were going to donate any proceeds to charity, so you want to make some money, how much should you charge people to play this game if you want to make money in the long run? Well, 350 is the expected value. So if you want to make money, you would charge anything above 350. Okay, so you could charge $4. If you charge $4, on average, you should make for yourself or for the game 50 cents. Okay, because the player averages 350 winning, and since they paid 4, you're profiting 50 cents per play. Now, do you ever actually profit 50 cents per play? No. But if you played this game 1,000 times, you would average 50 cents a turn. Which, if you think about that, if 1,000 people played it at 50 cents a profit per play, you just made $500. Okay, now, so this is kind of cool. You can design your own game and make money for charity. Where this really is interesting, this is what casinos do. Okay, the casino knows on every game inside their building what the expected value is. Okay, even on games like blackjack and stuff like that, every slot machine, they know what the average payout is going to be per player. So all they do is make sure they charge a little more, or sometimes significantly more, than the average win. And then all they need to do is get a bunch of people to play, and they make money. Okay? So to the casino, it's not gambling. It's just the law of large numbers. They know the more people play their games, the more people play slot machines, the casino gets, an average winning per play. And that's how they make money. Do some people win at the casino? Sure. Some people win. Most people lose. And in the end, if the casino wasn't making money, they wouldn't exist. So I kind of think of this as kind of like the law of casinos. Okay, casinos are built on that law of large numbers, where they know what's going to happen in the long run. To them, it's not gambling. Well, good luck with means and standard deviations of random variables.